and our prompt is humidification for bubble CPAP. A little bit of background. So neonates born with underdeveloped lungs require positive pressure airflow to prevent lung collapse. This allows for more air and more oxygen to flow into the lung tissues and allow for oxygenation. So Pumani is a low-resource bubble CPAP machine that we discovered that was also developed at Rice University. However, there is no readily available sterilizable humidifier for low-resource areas. And so this humidifier is key in allowing water droplets to be incorporated into the airflow, and this prevents drying of mucous membranes. A lack of humidity in the air can start to damage lung tissues, and that's something we don't want, especially in a neonate that is already having health issues. So problem definition. So our problem is neonatal care in low-resource areas need a way to sterilize and humidify water for use with the bubble CPAP machine. So this is going to involve inline humidification. We need to ensure a clean water supply. This is aimed at low-resource settings, which really have oxygen in the wall, which is something that we take for granted in the U.S. We want to design this system to be inline, standalone, and be able to tightly control the values of heat and humidity. So needs and targets, we need to be able to heat the water to sterilize it. It needs to be low energy, low cost, inline, and precise with its targets. The targets are a heater, which needs to be able to hit 27 degrees Celsius, which is an average for CPAP, and needs to incorporate a range of 25 to 35 degrees Celsius at a minimum. So the bubble CPAP intake pressure is 6 millimeters of mercury, so our system needs to be able to accommodate an inflow of air at that pressure. The humidifier needs to humidify the relative humidity of the air to 30 to 50%. The air and oxygen flow rate will be 5 to 10 liters per minute through the system, and the water required at target humidity is 0.053 to 0.106 milliliters per minute, which is approximately 100 milliliters per 12 hours. So our proposed system flow is the air coming from and O2 coming from the Pumani, going through the bubble humidifier, which is supplied with a water supply that has been UVC sterilized. This UVC subsystem includes reflective tape and covered acrylic housing to prevent exposure of any individuals to harmful UVC radiation. This humidified air will go from the bubble humidifier to the nasal cannula, and the nasal cannula will be connected to the bubbler, which is at the end of the bubble CPAP, and this creates a closed system and helps regulate pressure throughout the system. The bubble CPAP is also unique in that whenever pressure is changing in the system between the infants inhaling and exhaling, bubbles can be released to the end of the system, and this can help regulating pressure and help to allow the infants to exercise breathing a little bit more, and this has been shown to help infants get off of CPAP machines quicker. So our subsystem design going into the sterilization. So this will be an inline UVC LED sterilizing system. So it will need an energy requirement of 40 millijoules per centimeter squared. And so this is the capability of each of the UVC LEDs. We'll also have a particulate filtration system accomplished by a membranous filter, which will be over the inflow of the water into the filter in subsystem. And so there will be reflective tape around the inside of the housing, and this will allow for multiplication of the UVC effectiveness and allow the waves to really spread out across the entire container. This will require a 120 volt AC power system, and we'll be able to recharge this system and it can be used with a 9 volt battery as well. So the subsystem design in terms of the humidifier. So the humidifier will be an active bubble humidifier. Compressed air will be released into the bottom of the water column, and this will release bubbles to the surface. So the air is being forced into this water column, and then the bubbles coming up will have water droplets within it. And this is also going to be heated while this is happening. When you heat it, this makes the humidification process easier, and it allows for higher targets of humidity. Additionally, keeping it warmer and preventing condensation will allow for more water droplets to stay in the air and not condensate out. And so some other alternatives to this are humidifying via wicking materials or heating. And so Heating requires a lot of energy, which is not always available in low resource areas. And then wicking materials can harbor bacteria and would have to be exchanged frequently. And we felt like that would not be suitable for a low resource area, especially when the water is already at risk for having bacteria. And those wicking materials would have to stay sterile as well. So going more into our subsystem design, we decided that the airflow should be 5 to 10 liters per minute, and then the air in the system would be in the system for about 1 second. And so this goes into a bit more of our calculations. And so for the heating, we'll use 5 to 12 volt DC resistive heating element to accomplish this. So the power required to maintain steady water temperature with varying bubbler surface areas was calculated via MATLAB, and this shows some plots that we created. So power in terms of heating and sterilization. So the initial water heating will require a Q value of 100.3 kilojoules, and then the heat in 5 minutes will be 334 watts. The UVC bulbs were rated for 7 volts at 50 milliamps, and their power is 0.35 watts. So 15 bulbs will accomplish 5.25 watts. So battery capacity. So our sponsor helped us decide that rolling blackouts occur about every 4 hours for every 24 hours, just by his experience working in these low resource areas. So during the 4 hours, we foresee 2 heating and sterilization cycles plus holding temperature of water in the humidifier. So the total power will be 699 watts, and the average over 4 hours will be 318.17 watts. And so a 1D battery can supply 18 to 27 watts per hour. In terms of power, we want to utilize just simple wall outlet energy if we can. We want to pursue a rechargeable battery in case of the blackouts. Additionally, these batteries being able to be charged by solar panels can additionally be useful if there is not a better way to recharge the batteries in this area. But our design can really be compatible with all of these power sources. So in terms of getting inline feedback within our system, we want to use a flow meter to make sure that the flow rate is actually being accomplished. Going through the bubbler system could affect flow rate, so we want to ensure that it's being maintained throughout the system. We want to have a humidity sensor where we can maybe adjust the water temperature and or different aspects of the system to accomplish the humidity that we foresee will be useful, which is approximately about 50% relative humidity. We want the temperature sensor as a safety measure, making sure that the system does not get too hot and we're not flowing too hot of air into the infant and causing burns. And then we want a thermocouple sensor as well to control the water heating. So this shows our sensor placement. So the thermocouple and the bubble humidifier will shut off after a certain temperature is reached. Temperature sensor to regulate that. Humidity sensor coming out of the bubbler humidifier, and then a flow sensor right before the nasal cannula to understand what flow is being sent directly to the infant. And so here's some CAD that we designed to try to reflect what sort of prototypes we would want to pursue after this. And so this shows our system modeled after a standard canister. So after we started designing our system, we wanted to try to make it available through off-the-shelf components. So we imagine this being like a standard BMS medical container, typically used for hospital vacuum suction. And so these containers typically have at least 3 ports. So we want to utilize 2 ports for the inflow and outflow. So in this bottom left image, you can see the inflow coming in the left, the inflow coming in on the right. And so the air is being supplied into the top port, down deep into the water. And so the water level will generally be at about 75% capacity of the container. So it's going down here, and then there is a horizontal end effector on this, and this end effector has a bunch of small holes drilled in this cylinder, and so forcing the air down here and through this little perforated cylinder will allow for bubbles to be created, and then a lot of smaller bubbles will allow more surface area for the bubbles to get water transfer into them, and then so we have the humidified air coming out of here. And this is a top view of the system. Additionally, we designed opposed to a heating element, as we discussed earlier. We decided to do a heated sleeve over this container, and so this would allow for better heating and more control, since we are heating the entire container opposed to just the bottom of it. And it can also be removed if heating is not desired, or if there is no energy to power the heating at the time. All right, and so here's an animation of our CAD system. So as you can see, there's the heated sleeve, and that is our UV sterilization port. And so there are off-the-shelf components that are UV wands that you can stick into water bottles that are used for water sterilization. And so this wand can be stuck into the top port of the system. And so the system is thick enough to prevent any UVC radiation from going out in this small wand type application. And so after the wand is used to sterilize the water, which is also sterilizing the equipment, which is a double pro for us. And so once that is done, this wand can be removed as shown in the animation, and then a cap be placed over to seal the system once again. All right, and these are our sources. Thank you so much for your time, and we appreciate all you did to support this hackathon. Thank you.